Okay, this is lecture 17 of basic calculus 1. So, in the last lectures, we had discussed about differentiation and how to differentiate functions involving power functions and trigonometric functions. So, today we will be discussing a nice application of differentiation, which is about finding maxima and minima of functions. Okay, so, let us give first the idea of what is this maxima and minima. That is, as usual, it is the maximum of the functional value, that is the maximum of the function f. But always maximum may not exist. So, we have to really be careful while formulating it. So, it start with, suppose f is a function from D to R, D is a subset of R. In fact, we will not be considering any abstract subsets, but union of intervals. So, you may think of this as an interval now. Now, f is a function from D to R. Then we will say that f of x, or the function, has an absolute maximum at D in D if and only if f x is less than or equal to f d for every x in D. So, that is easy, because what we want is f of d is the maximum value of all the functional values. So, you take any f of x that should be less than or equal to f of d. So, instead of just maximum, we will say absolute maximum, because something else is coming. Okay. So, this is f of d will be called the absolute maximum of the function, and it is at d in D. So, that particular d we will say absolute maximum at D. Then x equal to d is also called a point of absolute maximum of f of x. So, absolute maximum is maximum value, and where it is attained, that is called a point of absolute maximum. So, similarly, you can define absolute minimum. Suppose A is a point where you think there is absolute minimum. So, that means f of A should be less than or equal to every other functional value. So, f of A must be less than or equal to f x for every x in D. And again, the point A is called the point of absolute minimum of the function f of x. So, these are fairly straightforward, coming just from English language, and both are called, if it is maximum or minimum, one of them, that is called an extreme point, or absolute extreme points, which are both A and D will be absolute extreme points here, and the function is said to have absolute extrema at these points, like the function has absolute maximum at D, absolute minimum at A. Similarly, it has absolute extremum at these points. This is just the terminology. So, corresponding to this, we have, as we told, we call that absolute. So, there is something called local maximum, which is slightly different from it, but that maximum thing should hold. Okay, sometimes absolute maximum is also called global maximum, absolute minimum, global minimum, absolute extrema, global minima, and corresponding to it, we have another notion called local maximum. So, what happens here? We will say that the same inequality holds, that is f of x is less than or equal to f c, c is a point, particular point in D. We will say that the function has local maximum at this point c, when every value f of x is less than or equal to f c, but now x does not vary over whole domain D in some neighborhood of that point c. Once for every point in some neighborhood of c, this inequality happens, f of x less than or equal to f c, we will say that the function has a local maximum at the point c, and the value f of c again is called local maximum value, and the point x equal to c is called a point of local maximum of the function f of x. Similarly, local minimum can be defined. Suppose you say B is a point inside D, you will say the function has a local minimum at B if f of B is less than or equal to f of x, where x varies over some neighborhood of B. So, that neighborhood of course should be contained in D in both the cases, for local maximum and local minimum, both the neighborhood should be contained inside D, otherwise we cannot say f of x. So, this is the notion of local maximum and local minimum. Again we say that x equal to b is a point of local minimum of the function f of x. Again both these things, maxima, minima, when use this local, they are called local extrema. So, local extrema means it is the values of the function which are local maximum or local minimum. Similarly, those points c and b, they are called points of local extrema. So, if you draw a graph, it will be easier to see how these notions translate to in terms of the graph of the function. So, suppose we have a function f which is defined on the closed interval a b to r. Assume that it is continuous. So, we have the graph like this. Then what we see that since it is a closed interval a b, then and it is continuous, our extreme value theorem says that it has a maximum, it has a minimum, and which are achieved for points in a and b. So, there exist points c and d in a b such that f c equal to maximum value of f x, where x varies over whole of a b. Similarly, f of d is minimum of f of x, where x varies over a of b, closed interval a b. Again such points c and d are the extreme points, and the maximum and minimum values are attained at these points. So, if you see, look at the graph, we have c which is here, and we have d which is here, and we have a. So, let us say where it is maximum here, the absolute maximum occurs at d. That is what we see from the biggest height of the function here, f of x values. So, at d we have the absolute maximum, and at a we have the absolute minimum, that is the smallest value, smallest vertical line or values of f. And you see that at c it is not an absolute maximum, it is not also absolute minimum, but it is some sort of maximum. So, that is what we say it is local maximum. If you take some small neighborhood, you can find always a neighborhood here of c. In that neighborhood, f of c is greater than or equal to all values of f x, where x varies over that neighborhood c minus delta to c plus delta. Similarly, if you consider this point E, here we have a local minimum. That is, you take, we can find a neighborhood of that E, say E minus delta to E plus delta, where f of E is less than or equal to f of x for whichever x you choose inside that neighborhood. So, this is how local maximum, local minimum, absolute maximum, absolute minimum look like. So, an absolute maximum can also become a local maximum, right, but converse is not always true. Some of the local extrema are not absolute extrema, as you see here at C and E. Okay. So, similarly, if you look at B, but you do not take as a neighborhood, only the left neighborhood is relevant here. So, left neighborhood of B is contained inside D, and in that neighborhood all the points, it is limited to this only now, from B minus delta to B. If you take any x, then f of x is greater than or equal to f of b. So, you may think of b as a local minimum, but it is not an interior point. Similarly, on the other side, if you take a, that is of course absolute minimum, but you can see also that is a local minimum, in the sense here the relevant neighborhood will be right neighborhood. You can find a neighborhood where f of x is greater than or equal to f of a. Of course, everything here, but that is similar to this last one b. So, that is how you find absolute maximum, but we do not know how to find really. That is how the notion says absolute maximum, absolute minimum, local maximum, local minimum, and these are all the extrema. So, we will be interested in finding the points where these are achieved, and also what are the values, what are the maximum, what are the minimum, and so on. Okay. So, if differentiability of f of x is assumed, then something more can be told about these extreme points. That is how we will apply the notion of differentiation to computing this absolute extrema or local extrema. First we will consider absolute extrema, we will come back to local extrema in a later lecture. Okay. So, in finding out this absolute extrema, or we have this particular statement which becomes very helpful. It is a theorem. What does it say? Suppose f of x has a local maximum and also has a local minimum, one of them you can take, either it has maximum or it has local minimum, that it f of x has a local extremum at an interior point C of the domain. So, suppose d equal to f is defined over d and d is a closed interval a b, then any point in the open interval a b is an interior point. So, this talks about the interior points only. If C is an interior point, then when can you say that C is an extreme point, a point of local extremum? So, it says, the statement says that if f of x is differentiable at x equal to C, that local extremum point, then f prime C must be equal to 0. That is what we have seen in the last picture. At C, we have a local maximum, we see that a tangent to the curve at that point C is horizontal. At E, we have a local minimum and there also the tangent is horizontal, which means f prime at those points is 0. It is differentiable, they are interior points then. So, it says that if you have a local point of local extremum at an interior point C and f is differentiable at that C, then f prime C must be equal to 0. So, we will see how to prove this. Suppose f of x has a local maximum at x equal to C. For minimum, argument will be similar, only the inequalities will be reversed everywhere. And we assume that C is an interior point of the domain of the function f of x. So, these are to be assumed. All that we want is to find that f prime C equal to 0. Okay. So, again our assumption is f x is differentiable at x equal to C. Now, since it is differentiable at x equal to C, the limit x goes to C, f of x minus f of C divided by x minus C exists. It is C plus h, x we are writing C plus h goes to 0. So, we say x goes to C, right. Our earlier definition h, definition of derivative, the h is here is taken as x minus C. Okay. So, limit x goes to C, f of x minus f of C divided by x minus C must exist. So, that means its left hand side limit, right hand side limit must exist and they are equal, which is the common value, that is we are writing as f prime of C. Okay. These two exist and they are equal. Okay. Now, let us, when you say x tends to C minus, that is left hand derivative. So, which says left hand limit x goes to C minus. So, that means if C is here, x will be somewhere here in some neighborhood of C, C minus delta to C. So, when you say C minus delta to C, then at that point f of x must be less than or equal to f of C. In fact, if since it is interior point, you can take the whole neighborhood C minus delta to C plus delta also, any some neighborhood of C, where whenever x varies over that neighborhood, then you will have the inequality f of x less than or equal to f of C. So, we will take both the cases, left hand limit and right hand limit, where this inequality is applicable, f x is less than or equal to f c. So, now let us consider the left hand limit first. So, x is less than C, it is varying over a neighborhood of C, left neighborhood. Then what we get is f x is, f c is maximum. So, f x must be less than or equal to C. Since f x is less than or equal to C, f x minus f c will be less than or equal to 0. The numerator here is less than or equal to 0. In fact, it cannot be equal, it is 0, let us say less than 0. Okay. And the denominator x minus c, that is also less than 0, right. So, you get f x minus c is greater than 0. Of course, it is, if it is equal, then we have no problem, the same argument goes through. So, for all x with x less than c, we have f x minus f c by x minus c is greater than 0. It can be equal also. If f of x is a constant function, then it can be equal also. But for the constant function, it is easy to see that f prime of c equal to 0. So, we do not need, or if you want to include, you can also write greater than or equal to 0. Okay. So, what we get from this is, even if you take greater than or equal to 0, what we get if you take the limit, since all these values are greater than or equal to 0, the limit also must be greater than or equal to 0 and the limit exists. So, this limit x goes to c minus f x minus f c by x minus c is greater than or equal to 0. Similarly, if you take the right neighborhood, that is consider all x with x bigger than c, then again the same inequality happens. F x is less than or equal to f c because f c is maximum. So, f x minus f c on the top is less than or equal to 0, but x is bigger than c. So, x minus c is greater than 0. So, you get L less than or equal to 0, right. Then when you take the limits, since it is less than or equal to, you get again limit x goes to c plus f x minus f c by x minus c should be less than or equal to 0. Now, the thing is both the limits exist. So, one is greater than or equal to 0, another is less than or equal to 0, and they are equal, that is equal to f prime c. So, f prime c must be equal to 0, right. Both the limits must be equal, and once they are equal, that must be equal to 0. That is the proof. So, this happens at an interior point c. Okay. So, for the minimum also, all these inequalities will be reversed. You say it is less than or equal to 0, f x minus f c by x minus c, and this is less than or equal to 0, this is greater than or equal to 0. So, again f prime c will become equal to 0. Okay. So, this really asks us to give some name to such points wherever the tangent is horizontal at an interior point. But we include some more points along with this. We say that an interior point c is called a critical point if f prime c equal to 0 or f x is not differentiable at x equal to c. So, that also we include, because we assumed there that f x must be differentiable at c, then f prime c equal to 0. So, if it is not differentiable, we also include that case. So, we say that an interior point is called a critical point if either it is not differentiable at c, or once it is differentiable, its derivative is equal to 0. Such a point is called a critical point, and it is defined only for the interior points. So, what our earlier theorem says is that if f of x has a point of extremum at some interior point c, then c must be a critical point, right, because if it is differentiable, f prime c equal to 0, if it is not differentiable, it is a critical point. So, anyway it is a critical point. That is what our earlier theorem now says, that if an interior point in the domain of differential function is an extreme point of the function, then it must be a critical point. If it is not a differentiable at that point, then also it is a critical point. Okay. So, now where to search for these extremum points? Suppose there is a maximum, then if it is an interior point, it has to be a critical point, right. It has to be a local maximum first. So, it is a critical point, and if it is not an interior point, say the function is defined over an interval, then it can be an end point, closed interval, then those end points. So, all that we have to search now for absolute maximum is critical points and the end points. These things will have some point where the function achieves its maximum value, and the same comment goes also for minimum values, right. And once it is bounded, our extreme value theorem says that it is the function's maximum and minimum values are attained. Now, where they will be attained? They will be either the end points or the critical points. That is how our search becomes limited. So, we will see how to do it, but first we should note that a critical point need not be an extreme point. It can be a false point for the candidate of maximum or minimum, like it can be local maximum for example, but it is not global maximum. We have seen from the graph, similar thing can happen, or it can also happen that it is neither, it is not even a local extreme point. We will see such examples. Okay. Well, let us see one first. Say f of x equal to x cubed. Now, once you differentiate this, it is defined all over R. So, every point is an interior point. Now, we differentiate say at any point C. So, we get f prime x equal to 3 x square. At C its value is 3 c square. Now, it has a critical point at x equal to 0, because this equal to 0 would give that C equal to 0. So, C equal to 0 is a critical point of this, but C equal to 0 is neither a maximum nor a minimum, right. You can see something like this, x cubed, is that fine. So, what does it say? Why it is not so? Because we can find out to the left of x equal to 0, the values of x cubed are negative. So, they are less than 0, that is they are less than f of 0, right. We say to the left every of f x is less than f of 0, and to the right x is positive. So, x cubed is positive, then you see that f of x is bigger than f of 0. Okay. So, that means f 0 is neither a maximum, because there are values to the right of it which are bigger. It is nor a minimum, because there are values to the left of this which are less than that. So, it is neither. 0 is not an extreme point, but 0 is a critical point, fine. So, that can happen. So, our search can be in vain, but our search will be limited. Now, that will help us in finding out the absolute maximum and absolute minimum.